All right, so for this problem, we got an electron placed 3 centimeters from a source charge of -3 nanocoulombs. What is the electron's acceleration when it's released? So a couple different concepts to think about, right? If we have an object that's accelerating, then it must be an unbalanced force acting on it, right? So we better be thinking, well, what force do we have on that electron to make it accelerate, right? And that gives you the whole F equals ma component, right? Well, they don't tell us it's on Earth or anything else, so let's assume there's only one force on it, and that's the electrostatic force. So we need to figure out the force on the electron first. Let's draw a picture. I've got a source of -3 nanocoulombs. All right, and so any source that's negative, a proton would be attracted to it, right? It has those inward field lines. But an electron, if I put my electron out here, there's going to be a field that acts to push it away. That would be the field E, and that field causes a force. The force on the electron, right, is equal to the field strength times the charge, right? So we can go about this one of two ways. We can find the strength of the field, or we can go directly into finding the force on the electron, right? So I'm going to go right into Coulomb's law. Coulomb's law says that the electrostatic force is equal to the Coulomb's constant times the charge of the first object times the charge of a second over the distance between them squared. Now in this problem they tell you 3 centimeters is the gap, and let's convert that to meters, 0.03 meters. So I can directly, with the information given, we know the charge of an electron, right? We know K, and we have the distance. We can just plug right in and find the force that is exerted on that electron in that field, right? And so that force, when I plug in the values, I have K, which is 9 times 10 to the 9. The units for K are newtons, meters squared per coulomb squared. 3 nanocoulombs, well, nano is 10 to the -9. They're the same thing. So if I want to convert to nanocoulombs, I can just say 3, convert from nanocoulombs to coulombs. Well, I can replace the n with 10 to the -9, and now I'm in coulombs, which is what I want. An electron is 1.6 times 10 to the -19 coulombs. So I'm in coulombs for all my charges, and notice that'll cancel with the coulomb squared of that K value. And I want to put it all over 0.03 meters, and that thing is squared. Right? So when you look at the units, I have coulomb squared canceling with the 2 coulombs. Again, that's why it's important to get out of nanocoulombs, so it cancels effectively. I have meters squared canceling with meters squared, and so my units give me units of newtons, which is what a force should be. And so now it's just a matter of calculating what the force is in my calculator. So I'm going to open that up here and type in my values. So I have 9 times 10 to the 9, 9 second e to the 9, actually I have that stored as K, times 3 second e to the -9. That's what times 10 to the -9 is the same as saying e -9, times 1.6 second e to the -19, all over 0.03 squared. And I get a force of 4.8 times 10 to the -15 newtons. 4.8 times 10 to the -15 newtons. So that's the force acting on the electron. And it's going to act to the right. Now let's look at what happens with our signs. In this case, technically, if I wanted to, I can put the signs of the charge in there, and negative would give you positive. Positive doesn't mean right. Now it happens to be to the right in this problem. Positive just means the electron will be repelled in that field. So just to clarify, for some of you guys that have issues with those arrows and the direction, this is why I don't like to put the sign in that numerator. I'd like to draw the picture And I drew the arrows in the picture based on the fact that I knew both those objects were negative and therefore they would repel. If it was positive and positive, you get a positive one. If they were positive and negative, regardless of which one is which, you would get a negative force, and negative means attraction between those two elements. So just to be really clear about how we go about using the sign of the charge in these problems. So not to be confused with what direction they're actually going. Now we're not done yet. So we know the net force on the electron, and Newton's law says that the sum of all the forces acting on an object are equal to its mass times its acceleration. Well, we know the mass. It's the mass of an electron. Well, that net force is the electrostatic force. The mass is the mass of an electron, and we want the acceleration. And so a little algebra tells you that the acceleration of the electron is going to be equal to that force over the mass of the electron. And so I can write into my equation 4.8 times 10 to the negative 15 newtons. The mass of an electron is 9.11 times 10 to the negative 31 kilograms. And I get a value. I'll make a little more space here in my page. For the acceleration of the electron, let's divide that by 9.11 second e to the negative 31. And I get 5.27 times 10 to the 15. And look at the units. I have newtons per kilogram, right? Remember, that was the strength of a gravitational field. And that, coincidentally, is the same as meters per second squared, which is probably a better unit to describe how the electron will accelerate in that field. So really high acceleration due to that really strong gravitational field.